Okay, listen closely, because we are about to completely change how you tackle your Cambridge Computer Science exams. Welcome to our ultimate explainer on mastering Paper 2A. Whether you are sitting syllabus 0417, 0478, 2210, or even AS level 9618, the strategy remains exactly the same. I want you to stop looking at a blank exam paper as a trap. Instead, think of it like a street artist looks at a blank brick wall. You need to make your mark. You need bold strokes of algorithmic creativity, but crucially, it has to be backed by incredibly solid, rigid structure. Without that underlying structure, it's just a mess. To understand what goes wrong, let's look at two typical students we see all the time. First, there's Alex. Alex is brilliant, knows every definition in the textbook, but in an exam, Alex panics and overloads every answer with raw computer science facts, totally ignoring the actual analysis the examiner asked for. Alex writes a massive paragraph when all that was needed was one sharp sentence. Then we have Sam. Sam is the opposite. Sam constantly watches the clock, rushes through, and completely misses the command word requirements, dropping massive amounts of easy marks along the way. Throughout this explainer, we are going to look at their flawed answers, picture all those red pen marks, and step by step, we're going to transform them into green check marks. We are reverse engineering the examiner's playbook.
Today, we're taking a daunting 100-mark paper and slicing it into 5 highly manageable strategic zones: validation and verification, code tracing and debugging, variables and arrays, database queries, and finally, logic gates.
Let's kick things off with Section 1, Validation and Verification. This is all about how we protect our programs from bad input.
So, how do we ensure data is actually correct? When faced with a question about data checks, Alex usually starts writing a dense essay on the history of data entry. Sam, rushing as usual, just scribbles down the word passwords and immediately flips the page. Both of them score absolute 0. Why? Because they aren't decoding the command words. The examiners are fiercely specific with their assessment objectives. They want to see that you can distinguish between automated, rigid system checks and human source matching checks. You have to prove you know the mechanics. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, so how do top students guarantee these marks? They use a structure.
This is where we introduce the Peel framework: point, evidence, explanation, link. Look at this exact breakdown. The strict, distinct difference between these two concepts is your golden ticket. Validation is the automated system checking if data follows the established rules. That is your point. What's your evidence? Things like a length requirement, a range check, or a data type check. The explanation? It ensures the data is actually reasonable or sensible before the system even tries to process it. Verification, on the other hand, is completely different. Verification checks if the entered data perfectly matches the original source document. The point is matching. The evidence is double-entry typing, typing it twice to see if the computer spots a difference, or a manual visual check against a physical piece of paper. The explanation is that verification catches human transcription errors. If Alex applied the Peel framework, that massive rambling essay would instantly become one sharp, high-scoring, undeniable sentence. And if Sam used it, Sam wouldn't drop the mark for missing the essential explanation.
Let's treat this like our first interactive workshop. Imagine a 60-second visual countdown timer right on your screen. I want you to perform a data scan on this table taken straight from the solutions for question 3. What is the core trend? We can see exactly how the examiner expects you to map these precise real-world descriptions to their specific technical names. Entered twice and match. That is fundamentally about checking against a source, so it's verification, specifically a double-entry check. 8 characters long. That is a hard mathematical system rule, so it's validation, specifically a length check. What about display on screen to be confirmed by human? That's verification, a visual check. And finally, value between 8 and 12 and only contain numbers are strict system constraints. Those are validation checks for range and type respectively. Spotting these patterns rapidly is what separates average grades from top-tier success.
Moving into Section 2, Code Tracing and Debugging. This is the core skill of proving your logic actually functions in the real world. Let's talk about testing for absolute robustness. Imagine an algorithm designed to only accept values between 30 and 40 inclusive. When Sam gets this question, Sam scribbles down, test it with 35 and 50. And again, Sam loses marks. It's just too simplistic. To guarantee top marks, you must step through 3 specific, highly deliberate types of test data. First, normal data, like 37. This proves the program accepts a perfectly valid everyday input. Second, and this is absolutely crucial, boundary data. You have to test the exact razor-sharp edges of your logic. If the range is 30 to 40, 30 must be accepted, but 29 must be firmly rejected. Testing these specific limits is the only way to prove to the examiner that your conditional operators, like greater than or equal to, are coded flawlessly. Finally, abnormal data. You throw in a 67, or even better, a random letter of the alphabet, to ensure the program rejects it gracefully without crashing the whole system. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Now, look at this trace table. This brilliantly illustrates how we officially document that rigorous testing. When you evaluate a password checking algorithm, trace tables like this one from the source paper are used to meticulously track the state of every single variable step by step during execution. Look at how the variables password, password up, symbol, and counter are logically laid out. Let's trace it. The input is my password. The algorithm first converts it to uppercase, checks the length, and then the counter variable steps through every single character from index 1 up to 11 to hunt for a symbol. Because of that exclamation mark at the end, the Boolean variable symbol flips to true at step 11, and the final output triggers as accept. If you rush this process like Sam, you'll inevitably skip an iteration step and ruin the whole table. You have to trace it line by line, simulating exactly how the computer's processor executes the code.
Let's jump into our next interactive challenge, find the flaw. The examiner provides pseudocode designed to input 15 negative numbers and calculate the largest negative number among them. But there are 5 critical logic errors intentionally planted in the script. The question is, are you just passively reading the code, or are you strategically applying the examiner's playbook? I want you to read this like a compiler hunting for syntax and logic faults. Let's visually debug this together and see how top students apply analytical thinking to completely deconstruct a flawed algorithm.
Okay, time's up. Here are the exact 5 corrections that earn the green check marks. First up, initialization. The broken code sets the variable large to 9999, but think about it. We are hunting for the largest negative number. If you start your baseline at positive 9999, every single negative number inputted will technically be smaller, so your maximum value will literally never update. Large must be initialized to an impossibly small number, like negative 9999. Next, look at the counter. It starts at 50, but the loop condition says while counter greater than 50. That loop is dead on arrival. It will never run even once. The counter must start at 0, and the condition must logically be while counter less than 50. Then, check the data entry validation rule. It says until negnum greater than 0. Wait a second, the prompt specifically asks for negative numbers. It absolutely needs to be until negnum less than 0. Finally, inside a while loop that's supposed to be counting upwards to 50, the counter has to increment. It needs to be counter equals counter plus 1, not minus 1. This is the ultimate trap for Alex. Alex would write an entire paragraph defining what a while loop is. But the examiner doesn't care. They just want you to identify the specific line, state the error clearly, and provide the exact functioning correction.
Section 3, Variables, Constants, and Arrays. This is where we define exactly how our programs store and organize all this complex data. When a Cambridge examiner asks you to define these foundational terms, what core trend are they actually searching for? The core trend, the absolute crux of the mark, is the state of change during execution. The exam explicitly defines a variable as a value that can change while the program is actively running. It contrasts completely with a constant, which remains permanently fixed and does not change its value during execution. Think about declaring class size as an integer variable because students might leave or join, but setting max class size as a constant fixed at 30 because the room physically cannot hold more desks. The examiner is rigorously testing your precision of language right here.
Now, how do we handle massive, overwhelming amounts of data without crashing our code? We use arrays. An array is defined as a data structure containing several elements of the exact same data type, all accessed using the same identifier name. I want you to visualize a massive metal filing cabinet. Every single folder inside has the exact same main label, but a unique sequential index number. A 1D array is just a single list of folders, while a 2D array is a grid of rows and columns. This theoretical definition is usually where Alex shines, writing down perfect textbook facts. But as we'll see, Alex often completely struggles with the actual implementation of this concept.
So let's look at that implementation with a speed writing challenge. Imagine a 30-second timer. If Sam was asked to clear an array of 10 names, Sam would panic and literally write 10 separate lines of code. My name 1 equals blank, my name 2 equals blank. The flaw there is massive inefficiency. As demonstrated in the source paper answers right here, the incredibly powerful advantage of arrays is using an integer variable, in this case index, to efficiently populate or wipe the data using simple, elegant repetition. The for loop iterates from 1 to 10, utilizing that index variable to dynamically access my name 1, then my name 2, automatically stepping all the way to 10, setting each one to a blank string. The advantage? A massive, bold reduction in code complexity.
Section 4. Database queries with SQL. This is where you can rapidly secure structured, undeniable marks if you know the formula.
Look at the plant sale database from the actual exam paper. We are handed a set of fields, and we need to logically assign and justify their data types. Plant price must be set to currency, because the reason is it needs to be displayed clearly in dollars and cents. Plant height has to be real, not just an integer, because a plant height of, say, 1.5 meters absolutely requires decimal precision for any future calculations. Position is Boolean because in this system it only has two absolute binary states. It's either in the sun or it's in the shade, true or false. And when the examiner inevitably asks you to select a primary key for this table, you choose Plant ID because it uniquely identifies each individual plant record without any mathematical chance of duplication.
Now, let's write a query with total efficiency. You are given a complex-sounding requirement. Display the names, prices, and number in stock of all plants taller than 1.8 meters. Using our exam strategy, we don't panic, we just break SQL down into 3 rigid logical steps. Step 1, what exact fields are we showing? Select plant name, price, stock available. Step 2, where does this data actually live? From plant sale. Step 3, what is our mathematical filter? Where plant height greater than 1.8. Do not overcomplicate this. Do not write a paragraph explaining how databases work to the examiner. Just hit the 3 commands with perfect syntax, collect your marks, and confidently move on to the next section.
Section 5. Logic gates and expressions. We are stripping computing down to its rawest, most fundamental form, Boolean logic. Question 12 drops this seemingly terrifying logic expression onto your desk. X equals A and B exclusive or not B and not C. When Sam sees this, absolute panic sets in, but we are going to use the playbook. We just break it into manageable brackets. The left side is nothing but a simple AND gate combining inputs A and B. The right side is another AND gate, but this one is combining the inverted signals of B and C. And finally, those 2 distinct isolated subcircuits are joined together at the very end by an XOR gate. It's just a sequence of small puzzles.
By breaking the math down, we can draw the interconnected logic circuit effortlessly. Look at the flow of data in this diagram. Inputs A and B flow directly, unmodified, into the top AND gate. Then, the B signal branches off, travels through a NOT gate, and meets the newly inverted C signal at the bottom AND gate. The distinct outputs of these 2 AND gates become the maximum 2 inputs allowed for our final, decisive XOR gate, which outputs the final value X. It is not a messy, chaotic web. It is a highly structured, beautiful flow of Boolean logic.
And relying on that strict structure is exactly how we perfectly calculate the truth table. A truth table systematically grinds through the working space for every single possible state of inputs A, B, and C, starting from 0, 0, 0 all the way down to 1, 1, 1. By methodically applying our expression, we prove the final output X is 1 when all inputs are 0, specifically because the right-hand not B and not C condition triggers the final XOR gate. It also outputs 1 when specific combinations like A and B are active. The ultimate secret here? Use the working space columns provided on your exam paper. Do not try to hold all these Boolean flips in your head. Write down the output of the first bracket, write down the output of the second bracket, and only then apply the final XOR. That methodical step-by-step process is exactly how you eliminate those silly grade-dropping mistakes.
So look at what we've achieved. We have successfully reverse-engineered the entire exam paper. We've translated scattered, overwhelming questions into a unified framework. Our complete computer science success blueprint relies on 3 rules that guarantee top marks. Rule 1, command word decoding. Know exactly what the examiner is asking. Rule 2,
Peel framework application, structure your logic so it's undeniable, and Rule 3, the time management matrix, don't rush like Sam, but don't overwrite like Alex. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. The next time you face a complex pseudocode problem, ask yourself, are you just reacting to the code, or are you strategically making your mark with bold strokes and solid structure? Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.